SciMax Technologies is a small innovative company with hands-on talent in optimizing state-of-the-art composite structures technologies, especially in thermoplastics. We are proficient in 3D design, structural analysis, utilizing finite element analysis and finite element modeling. SciMax integrates tooling design, fabrication, and validation testing. Our team members herald from the industry primes, with experience in advanced composite programs such as the CH-53K King Stallion, the AH-64 Comanche, both JSF contenders, among others, as well as commercial aircraft. Our engineering team averages over 35 years of experience in aerospace composite structures. We have a small facility of about 2,000 square feet and are looking to expand with future contracts. SciMax collaborates with academia such as the University of Maine and Vaughn College of Aeronautics in New York. A common issue in all aircraft is the performance weight challenge. Therefore, the goal set out by our design team was to bring weight down in order to attain improved aircraft performance. This results in increased payload and longer range while maintaining or improving integrity and durability. The lightweight flooring system development was part of the NAVAIR contract under PMA 261 to obtain lighter and more robust flooring system for the Navy and Marines. The goal of the program is to create a flooring system for the CH-53K under 1,500 pounds while meeting all performance specs. The programs were initiated in a building block approach. First, material selection was conducted via analysis and coupon level validation testing to select the best material. The preferred material selected is a polyether ether ketone resin with an AS4 carbon tape, known as AS4 PEEK. This material has excellent impact resistance characteristics over other thermoset and thermoplastic systems. Next came aircraft element section design, with the design, fabrication, and validation testing of components. At the same time, innovative fabrication methods via tooling design, analysis, and tooling fabrication were validated. 10 subcomponents, some 18 by 20 inch and some 18 by 18 inch, were designated as prototype floor section panels. The panels were fabricated and tested for static loading, endurance loading, and impact drop testing. Once these phases were completed successfully, the program moved on to the design of full-scale prototype aircraft representative panels, or PARP. Further optimization was undertaken to further reduce flooring weight with the optimized PARP design, known as OPARP. Design and analysis of the PFS panels concentrated on ply stack-up symmetry and ply orientations to meet loading path requirements in a quasi-isotropic load path distribution, 0, plus 45, minus 45, and 90-degree orientations. FEA and FEM models were developed with static and dynamic impact loading simulation to predict panel performance under actual conditions. The lower half of this slide, from left to right, shows 4 by 5 inch coupon impact testing, bending coupon testing, and a single cell floor section setup for impact testing. The initial coupon level testing provided the confidence to proceed with the fabrication of the aircraft PFS panels. The fabricated aircraft PFS panels were subjected to static, durability, and impact testing by NAVAIR. Static loading testing was conducted by applying hydraulic pressure on a 10-inch steel disc placed on the panel. Pressure was increased until reaching 2,000 pounds, or 25 psi. After reaching the 2,000-pound load, with no measurable bending or deflection, the load was slowly increased up to 115 psi without any sign of failure, except for about a 1/4 inch deflection of the panel between the support rails. Failure did occur when the loading reached 128 psi. It should be noted that although static load is not the design driver, the large margin above the 25 psi specification was expected as part of the critical design to meet the impact loading tests. Durability testing was performed with a 2.5-inch wide, 4-inch diameter steel roller, rolling over the panel from edge to edge under a load of 1,000 pounds for 1,000 full cycles. It should be noted that the load concentration on the panel is only the wheel contact surface as it is rolling over it. The contact surface is estimated to be only 1/10 of an inch wide over the 2.5-inch wide steel roller. This translates to a dynamic load of about 4,000 psi. The tests were successful with only minor scratching of the panel surface along the wheel edges. The impact testing was the most severe test, which used a 200-pound wooden box with a corner blunted to a 1/2-inch radius and dropped from a 15-inch height above the panel. This yielded a 250 foot-pound, or 3,000 inch-pound impact on the panel. All impact tests met the minimum damage criteria of limited local delamination with an indentation into the panel no greater than 0.3 inches deep. Utilizing thermoplastic carbon flooring will yield a 350-pound weight savings per aircraft compared to the current machined aluminum flooring system on the CH-53K. Our most recent SBIR contract came to a close at the end of 2023 with a mature design and fabrication methodology. The TRL level at this stage of the development is in the 7 to 8 range. SciMax has continued further with its own research and development to optimize the thermoplastic fabrication process. This new process will lead to improved accuracy by using internal heated air pressure in an encapsulated hard tooling, thereby eliminating the need for the expensive platen press. This will simplify the fabrication process, reduce recurring labor by 25%, improve and optimize integrity and repeatability of the product, reduce scrap factors, and provide a better production-ready flooring system at a reduced price. The research and development phases provided SciMax with a strong learning path on how to optimize fabrication methodology for thermoplastic flooring. This can be summed up in 4 major steps. While the autoclave process was successful, it proved to be expensive with sizable reworks due to difficulty in high-temperature bagging, which could lead to a high scrap factor. Additionally, this required an expensive high-temperature and high-pressure autoclave, rated at 800 degrees Fahrenheit and 300 psi. SciMax next transitioned to a heated high-pressure and high-temperature platen press concept. The press provided the vertical forces coupled with a spring-loaded bolted sliding rail system for the lateral pressure, providing 3-dimensional heated consolidation pressure. This system worked well. However, the spring loading was sensitive to the accuracy of torque values of the spring-loaded bolts, and monitoring torque values was limited during the consolidation. In the third stage, the mechanical lateral loading system was replaced by an optimized pneumatic piston that pushed the sliding tooling rail against the panel, with very good results. All the PARP and OPARP panels were produced using this method, which also had shortcomings. Adjustments would be needed when moving from press to achieve good parallelism between the upper and lower platens of the press. The ideal tolerance of plus or minus 0.005 inches on a big moving press assembly is a challenging task, and a good close tolerance high pressure and temperature press is expensive. Therefore, further enhancement is needed to achieve production level repeatability, lowering fabrication cost. This led SciMax to develop a proprietary consolidation system that requires only a high-temperature oven to attain an optimum production setup. We call this new patent-pending methodology to fabricate the thermoplastic floor panels the internal pressure oven consolidation, or IPOC process. Hollow steel mandrels sleeved with high-temperature elastomer are mated to an outer concave tooling assembly. The system is sealed and pressurized from a single source, pressing uniformly against the net shape of the outer tooling assembly, forming the outer mold line, or OML. The system operates in a high-temperature oven, with heat and pressure applied per consolidation specifications, and monitored throughout the consolidation cycle. The resulting fabricated panels are matched die fabrication, with accurate net dimensions that are so critical to aircraft cargo flooring. Transition to fleet will require a final validation of the IPOC fabrication process. The estimated budget to validate the IPOC process would be less than $1 million. A notional program spanning approximately 12 months would include a robust feasibility study via fabrication of about 6 to 10 panels, followed by validation testing to assure that the updated process meets all the performance specs. The IPOC process would meet the weight reduction for the PARP and OPARP and demonstrate optimum cost reductions. The predicted production cost using IPOC would be in line with typical composite structure cost for aircraft in dollars per pound, and most likely even lower, with elimination of expensive machinery and reduced labor hours. This will be a marketable product for multiple vertical lift platforms, including the V280, CH-53K, and any retrofit for current in-service cargo aircraft and helicopters, such as the C-130, C-17, and CH-46 derivative, among others. While the current configuration is based on the CH-53K, transition to a fleet program on other platforms would require significantly minimal effort, with just an initial configuration adaptation and validation to the aircraft. Production of the flooring panels with the IPOC process will require a much lower capital investment for the fabrication shop. No expensive equipment will be needed, with only basic machinery required, such as an automated ply cutter, 2 medium-sized 800-degree rated ovens for redundancy, and a basic cleanroom, all fitting in a facility of about 2,000 to 2,500 square feet. Market analysis indicates that once SciMax sets up a thermoplastic fabrication facility with the IPOC philosophy, SciMax Engineering can provide multiple DoD programs and commercial aircraft structural components susceptible to high impact. These include areas of flight safety concern, such as leading edges of wings, horizontal and vertical stabilizers, jet engine inlets, fuselage lower surfaces for aircraft taking off and landing from unimproved runways, and more. We invite you to consider the IPOC design for your impact resistance requirements. Thank you for joining today. If you have any further questions, please feel free to reach out to us. We look forward to discussing your needs and requirements.